Alright, so let's get into the rules of probability, section 5.2 from the textbook that we are using. So we are going to split this into two separate videos, first of which we are going to be describing chance behavior with a probability model and defining and applying some basic rules, and then we'll look at two-way tables and Venn diagrams and how we can use them to determine some probabilities. So in the previous section, we used simulations. We designed simulations and we used them to find probabilities. But that's kind of a pain. That's kind of time consuming. We don't have time to do that all the time. So we can use other things to help us find probabilities of a particular outcome. A description of chance behavior contains two things. It contains a sample space of a chance process, and that sample space is all possible outcomes. And then it will also talk about a probability model which has the probability of each thing in the sample space. And we'll see what this looks like in just a second. So here we have rolling dice. We're going to roll two dice. They're fair dice, meaning no one side is more likely to come up. They're regular six-sided, and one's red, one's green. You see them down here in the corner. If we roll these die, these are all of the possible outcomes that we could get. And there are 36 different things that could happen. So our sample space has 36 total outcomes in it. And since the dice are fair, each one of these outcomes is equally likely, so each one of these possible combinations of dice has a probability of 1 over 36. A probability model will allow us to find the probability of any collection of these outcomes. And we have to define something called an event. An event is any collection of outcomes from some chance process, rolling dice. That is, an event is a subset of the sample space. And usually we use capital letters to denote events. So for instance, if A is some event, we write its probability as P parentheses A, probability of A. If we define A to be a sum of 5, these are the things that match that event. These are the outcomes. This is the subset of our sample space that match with this event. Since there are 4 outcomes that result in a sum of 5, and each one has an equal probability of 1 over 36, the probability of A, that is the probability of getting a sum equal to 5, is 4 out of 36. If we defined event B as being a sum that's not 5, think about what the probability of B would be. Go back to look at your sample space for the rolling of 2 dice and see if you can figure this out. Well, if you're smart, you didn't count all of the different ways we don't get a 5. We can take 1, the probability of anything, of something happening, minus the probability of getting a sum equal to 5. So 32 out of 36 is our probability of not getting a 5. So let's talk rules. First one, no surprise. Probability is between 0 and 1. And in a probability model, all possible outcomes together must have probabilities whose sum is 1. Something's going to happen all the time. All of the different possible things that could happen should add up to 100% of the time. And if all outcomes are equally likely, the probability that A occurs can be found using the formula number of outcomes corresponding to event A over total number of outcomes in sample space. I like to think of this being as possibilities divided by totals. The probability that an event does not occur is 1 minus the probability that it does occur. And if 2 events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. And another definition, mutually exclusive, also called disjoint events, have no outcomes in common and so can never occur together. Rolling a sum of a 4, rolling a sum of a 5 are two mutually exclusive events. You can't roll 2 dice and get a 4 and a 5 at the same time. It's just not possible. So here's some notation for this. For any event A, probability of A is between 0 and 1. If S is the sample space, the probability of S is equal to 1. Probability of A is the possible ways to get A divided by the total things. The complement rule, the probability of A complement is equal to 1 minus the probability of A. Another way that you see this written is probability of A apostrophe. That means the same thing as a C. Depending on what you're looking at, you might see one or you might see the other. And if we have mutually exclusive events, the probability of one or the other happening is just the sum of the two things. For instance, the probability of getting a 4 or a 5 sum, we would take the probability of getting a 4 plus the probability of getting a 5 and add them together. So here is a probability model for distance learning courses and different ages that are in college. So the probability of somebody who's 18 to 23 taking a distance learning course is 0.57. So we want to do two things. Show that this is a legitimate probability model, and then find the probability that a chosen student is not in the traditional college age group. That would be 18 to 23. Well, how do we do that? Well, pause the video and see if you can't do this on your notes right now. So it's a legitimate probability model because each probability is between 0 and 1, and the sum of all of them, all the possible outcomes, is equal to 1. Those two things together make this a probability model. You need both of them. And the probability that a chosen student is not in the traditional age group would be 1 minus the probability that they are. So 1 minus 0.57. Or, ladies and gentlemen, we could have done the probability of being 24 to 29, or 30 to 39, or 40 and older, and since these three events are mutually exclusive, there can be nobody overlapping in both groups at the same time. We add these three things together, and we will get the 0.43 that we found down here. So that's where we shall stop for today. Remember, to be a probability model, you do need two things. Have a glorious afternoon and evening.